Now we are going to start talking about two or more random variables, and this leads us into joint and marginal probability distributions. Let's revisit an example from a couple weeks ago when we talked about conditional probabilities. During a few wintry months in Boulder, Jim collects the following data where he observes whether or not there's snow overnight and whether or not the bus is delayed as a result. We have a total of 60 observations here. Based upon that, what's the probability that the bus is delayed and there is snow overnight? The probability that the bus is delayed and there is snow overnight would be 5 over 60. What is the probability that the bus is not delayed and there is not snow overnight? This probability would be 36 over 60. So we can take our observations and divide by the sum of all the observations, which is 60, to get something known as a joint probability distribution function. So we denote this as the joint probability distribution for two random variables. This is known as the bivariate distribution. We refer to this as f subscript xy of x and y. And for discrete variables, this is known as a joint probability mass function, in contrast to a joint density function for continuous variables. If we plotted this three-dimensionally, we have the x-axis, whether or not the bus is delayed. We have the y-axis, whether or not there's snow overnight. And we can have a frequency. If we divide each of these frequencies by the total number, and that's 60, we come up with the joint probability mass function, fxy of x and y. Each of these columns or bars tells the probability of that combination of buses being delayed and snow overnight. So for example, we can calculate the probability that the bus is not delayed and there's not snow overnight by just calculating the height of that bar in this three-dimensional plot. There's a couple important things about a joint probability mass function for discrete variables. Similar to probability mass functions and probability distribution functions for a single random variable, the joint probability mass function always has to be greater than or equal to 0. Similar to how the sum of all fx's has to equal 1 for a probability mass function of a single random variable, the double summation over all x's and all y's has to equal 1. That's what I was just referring to here, where the sum of all of these bars has to equal 1. If you want to calculate the probability that x is exactly equal to some number and y is exactly equal to some other number, we can just substitute in to the joint probability mass function those values of xi and yj. And that's what I did earlier when I calculated the probability of this large bar being 0.60. Let's go through an example. An auto assembly task performed by robots. These robots are welding 2 joints and they're tightening 3 bolts. X represents the number of improperly tightened bolts, and Y represents the number of defective welds. We can put together this joint probability mass function where we have X on the top and Y on the bottom. And we've got the number of improperly tightened bolts going across the top, the number of defective welds going down in the rows. The vast majority have 0 improperly tightened bolts and 0 defective welds, but then we have different combinations of X and Y, and together these 12 different possibilities represent the joint probability mass function. The sum of all entries has to equal 1. Also, all probabilities have to be greater than or equal to 0, which they are. And we can ask things like, what's the probability that x equals 3 and y equals 1? That's also known as fxy of 3, 1. And that's just the probability when x equals 3 and y equals 1, we get 0.002. We can do the same thing for a joint probability density function for continuous variables, density instead of mass. The joint probability density function always has to be greater than or equal to 0. Instead of double summation over all x's and y's, we take the double integral. So the double integral over x and y has to equal 1. The volume under the curve has to equal 1. Instead of representing this graphically by bars, we can represent it sort of as a volume. So we might have a surface like this, and then going in the y-axis, we might have another curve. So it's basically like a bowl or a mountain. Can't really tell from my drawing, but it's a three-dimensional surface. And you can calculate probabilities based upon integrating this three-dimensional space over x values and y values. And let me show you an example of that now. In healthy individuals, ages 20 to 29, calcium level in blood is between 8.5 and 10.5, and the cholesterol level is between 120 and 240 mg per deciliter. X is the calcium level, Y is the cholesterol level. We are assuming a uniform distribution for both of those variables. So if you just looked at X, it's uniformly distributed. This is not to scale, but between 8.5 and 10.5. And similarly, for the cholesterol level, it's uniformly distributed between 120 and 240. Assuming a uniform distribution for those joint variables, what is the joint probability density function fxy of x and y? Well, it's going to be some constant. In other words, if you took a look at this three-dimensionally, we have x, y, and fxy, then it's essentially this just a slab or a small rectangle where x has a domain. This is, again, not to scale. X can go from 8.5 to 10.5, and y can go from 120 to 240. And our job is to find c. Well, we know that the integral of our fxy dx dy has to equal 1. Our joint density function is c. And so if we integrate x from 8.5 to 10.5 and y from 120 to 240, if you did this integration, you would end up with c times 240 minus 120 times 10.5 minus 8.5, which is 240c. And if that has to equal 1, then that simply means that c equals 1 divided by 240. So 1 divided by 240 is the joint probability density function for these two variables. Let's look at another example. We can calculate probabilities, and probabilities we can also get from the double integration. What is the probability that x lies between 9 and 10 and y lies between 125 and 140? In other words, what we're trying to find is this probability that x lies between 9 and 10 and y lies between 125 and 140. Going back to probability we can get from double integrating or calculating the volume underneath a curve. We integrate over y first, integrating y 125 to 140. Inside that, we integrate x. So we're interested in 9 to 10. Our joint probability function is 1 over 240, and that's dx dy. The inside here is just going to be 1 over 240. So then we're going to have the integral of y from 125 to 140, and that's 15 over 240, or 0.0625. That means that if we randomly selected somebody based upon this joint probability density function, there'd be a 6.25% chance that their calcium level would be between 9 and 10, and their cholesterol level would lie between 125 and 140.